right now because of the fires that have been occurring in the Western United States. And these have been some of the worst in history. And they've produced red skies and terrible air quality for weeks. But we should keep in mind that this actually happens every year. So you can see 2015 through 2019 images of each of these types of fires. So we at Kids Making Sense, we really saw this and see this as an opportunity for you to teach science through the lens of smoke pollution to your students. And so this year, the wildfire was a little different. The season started early, and the immense heat from the fires lifted the smoke high into the atmosphere through thermal lift. And if we go to the next slide, and we'll see that because it was lifted so high into the atmosphere, the smoke has basically blanketed across the entirety of the United States. So this is no longer just a local problem. We've actually managed to impact the entire continent. And so we believe that science teachers, so no matter if you're here in the West or anywhere across the country, because as we just saw, this is not just a local issue, can really use these sorts of annual wildfires to teach science through the lens of smoke pollution. And we know that there's a lot of sources available to you as science teachers and also as individuals to interpret smoke and to sort of try and understand air quality for you and for your classes. So we're hoping today to walk you through some of those resources that might be useful for use in the classroom. And also we'll discuss the topic of wildfire smoke and particulate matter more broadly as well.
And my name is Bastian Scholl. We'll introduce ourselves formally, but before introducing ourselves as staff member, I wanted to let you know that I'm delighted that you've all taken the time to join us tonight. I'm also delighted to be joined by my colleagues, Olivia and Tammy, as presenters. A little bit of background, the Kids Making Sense program is a science educational program whose aim is really to instill best practices of science and science through science education using the topics of air quality and other environmental topics. We provide a program that gives you curriculum and sensors that let your students interpret data they collect and learn how to take action to reduce emissions and exposure in their environment. The program was created and is being run by very passionate and experienced engineers and air quality and atmospheric scientists. We are very passionate about using these key environmental topics to teach science. Also, as a bit of background, the program and its tools have been developed over a number of years in collaboration with other environmental agencies and groups, and has been used in a large number of classrooms, both in the US and abroad. And I just wanted to introduce us as a program and then introduce us as a team. I'll turn it over to my colleagues. My name is Bastian Scholl. I am one of the product managers we have here. And as I said before, I'm joined by Olivia Ryder and Tammy Levetzo.
Yep, so I'm Olivia. I'm one of the co-program managers. I'm also an atmospheric scientist. And
hello, I'm Tammy Levetzo. I am a co-program manager with Sonoma Technology. I'm a senior scientist. And I've actually been studying air quality issues for about 20 years. And I have been very active in the Kids Making Sense program. I've worked with lots of teachers in many classrooms over the last several years. So welcome everyone and thank you for joining us.
That's great. That's I'm honored to be joined by such a capable team. I think just as we'll see as it breaks out here, I do a lot of our tech development. My focus is on technology and applying it to the learning process. And Olivia and Tammy are much more focused on the science and the interaction with teachers and enabling you teachers to teach good science. And so with that, we'll go ahead and really get into the heart and the subject matter of the presentation. And I'll just walk us through the agenda and then turn it over to Olivia for starters. So today, what we wanted to accomplish, we wanted to teach you as teachers about what is in wildfire smoke. That's a common question that we have gotten. We want you to understand the air pollution basics. How is it measured? What are the health standards? Where can I learn more about the AQI, for example? A key other part of our program today is that we wanted you to become aware of air quality resources. And by resources, we mean informational resources. And as we said in the invite, where that show the air quality and all the smoke effects in your community, let you measure them in your community or assess the measurements in your community. We'll talk a little bit about you can potentially even measure things in your community. And then we'll transition a little bit to how our program has really a very strong connection to all of the subject matter. So as just a short housekeeping item, we would ask that you use the Zoom Q&A feature, which you can find among your functions in Zoom, to ask your questions that you might have during the webinar, and we have set aside time at the end of the webinar to answer those. So with all of that, we'll go ahead and turn it over to Olivia.
Thank you, Bastian. So before we jump into wildfires and the issues that we have with wildfires and air quality, let's first take a step back and think about more generally what air pollution is. So when we think about air quality in this normal sense, we might consider typical pollutants, which are also known as criteria air pollutants. So those include ozone, particulate matter, nitrogen dioxide, sulfur dioxide, carbon monoxide, and lead. And these are well regulated by the government, so under the Clean Air Act. And their sources and the amount that we might expect to find in the air at any given time is generally well understood. We understand where they come from, we sort of understand the fate of them in the atmosphere. However, when it comes to these wildfire events, if we click through to the next slide here, there we go. For the wildfire events, these are much more regional and local. And they have some major air pollutants, including particulate matter, which dominates. They also have carbon monoxide, NO2, and other air toxics, which we'll talk about in a second. But the locations and the intensities of these sorts of events, being fires, are very variable. And these naturally occurring wildfires also occur during exceptional weather events like we just experienced here in the West. So dry lightning causing them, they can be exacerbated by strong winds and other sorts of weather. They can also create their own weather systems. So if we think a little bit more specifically about wildfire smoke, we might ask, well, what's actually in wildfire smoke? It's been a hot topic recently, but do we really understand what it's made of? And what are we breathing in? That's kind of an important question to be asking for yourself and for your students. And so the answer is actually, it kind of depends, which is not a super satisfying answer, but unfortunately it's the one that we have. So smoke composition, it's really going to depend on a number of factors that include, so what exactly is burning? So if it's grass or if it's brush, those might be different compositions than if it was a tree or a building, for example. So if it's buildings, you've got a lot of materials to think about. They might include lead, they might include metals, toxics, all sorts of things. It's also going to be dependent on how efficiently the fuel is burning. So whether it's burning more clean and hot, or if it's a dirtier, wetter, moisture-rich source that is burning. Wind and weather conditions are going to play a big role, as is how old the smoke is. So if you're very close to where the fire is occurring, you're going to have a different, the smoke is going to be a different composition than if it's aged in the atmosphere and had time to sort of react with other things that are present. And, maybe it's the next state over, that's going to have a very different composition. So these are all sorts of factors that play a role in what exactly the composition of wildfire smoke is. But having said that, we can sort of, and you can see in this picture here, boil it down to these general categories of species. So the largest pollutant that we are concerned with being particulate matter. You also have carbon monoxide, nitrogen oxides, and these other components as well. So if we go to the next slide here. So since, as we've said, particulate matter is a main component of wildfire smoke, and it dominates the air quality index and measurements during these large fire events. Let's talk about what it actually is briefly. So it's a complex mixture. So particulate matter is defined as a solid or a liquid that's suspended in the air. So it could be composed of many different compounds. It could be up to thousands of different things. It could be emitted directly, or it could be formed in the atmosphere. And then the sizes vary tremendously. So this image that we're seeing here is in the dark gray, you have a human hair. So that's around 50 to 70 micrometers in diameter. And you can see that coarse particles, so PM10, like dust or pollen or mold, those are quite large. Those are 10 micrometers in diameter across. And then there's these very fine particles like soot or organics or metals that are around 2.5. We call them PM 2.5 because they're 2.5 micrometers in diameter roughly. And the size of these particles really does matter because that's going to determine what the health effect is in the body. So if we go to the next slide here, there we go. So the larger particles, which are being depicted in this image as the green circles, so those are going to be filtered out by the upper respiratory system. So they'll make it down through the trachea, but they'll generally be removed by coughing or sneezing or swallowing. It's these really small particles, the PM 2.5, that can reach further into the lungs and really can worsen asthma, can deliver harmful chemicals into the bloodstream. They can cross the blood-brain barrier. They can increase the instance of heart attacks and strokes. There's all sorts of health complications that could come from breathing in these very small PM 2.5 particles. And PM 2.5, I should point out, is actually one of the primary, so when a couple of slides back, we said that particulate matter was one of the main components of wildfire smoke. It's that PM 2.5 that we're really concerned with that's present in very high concentrations. So PM 2.5, if we put this into context here, it can be reported on a 1 minute to a 1 hour basis. And the health effects that have been attributed to PM 2.5 are largely based on if you were breathing in that air for 24 hours. But it actually, for 24 hours, right? But in some cases, such as when you have wildfires, you might have very high levels of PM 2.5, but for much shorter periods of time. And it turns out that the health effects of those sorts of exposures are actually less well understood, unfortunately. But having said that, we do have some excellent tools that we can use to determine what the air is like outside and if it's okay to spend time outside. So the first of those is the National Ambient Air Quality Standards. And the other is that you might be more familiar with actually is the Air Quality Index. So that one's going to tell you how clean or polluted the air is and what the associated health effects might be and if you should be concerned. So if we go to the next slide, great. So the Air Quality Index is this, it was established by the Environmental Protection Agency. And what it does is it takes the levels of pollutants outside and it translates it into a scale that runs from 0 up to 300, or in some cases above 300. And so basically if the AQI level outside is 0 to 50, that means it's good outside, you know, we should have no problems going out and exercising from a health standpoint or an air quality standpoint. Whereas if you get maybe down to 151 to 200, then you've got to start to take into account, okay, do I have health issues? Should I be concerned? What do I need to take into account? Do I have asthma? Things like this. So it's really a helpful table that translates the science into something that's much more digestible. It's also color-coded, which is key for communication to people. So if you see something that's orange, you know what that means immediately. If you see it's purple, you know what that means immediately. So it starts to become ingrained.
And I would just interject quickly, Olivia, that as we'll see throughout the remainder of the presentation, that a lot of the tools that we recommend as best practice and best of class consistently implement these color codes so that once you've remembered and memorized what they are, they're consistently used throughout.
Yep, that's a very good point. And in fact, during the wildfire events, PM 2.5 concentrations, they can significantly exceed the very unhealthy levels. You can get up into the hazardous levels, which actually has been the case in the Yosemite area in the past few weeks, which is concerning. So now that we've sort of talked about the AQI and the air quality index, what tools do you have at your disposal to sort of understand what your own personal air quality index might be, or the air quality index of your students? So in order to understand that, let's again take a step back for a second, and let's talk about how the government agencies actually measure PM 2.5. So where are these concentrations, where are these values even coming from? So the PM 2.5 is measured, well, when it's reported by government agencies, it's being measured with one of these instruments that you see in this picture. It's got an inlet, it's pulling in air at all times, and it's analyzing that air. The locations of these instruments are very carefully chosen. They're expensive instruments, they're hundreds of thousands of dollars, and they are being checked. They're, the data quality is being monitored at all times. Professional staff are there to fix them when they go wrong, make sure everything's being calibrated properly. So it's very difficult to sort of, throw one of these on every corner and just, have a whole bunch of these across the country. That's unfortunately not feasible. So the data that is being collected using these is sort of to give a regional air quality map, and sort of help to see if there's any sorts of regions that have egregious outliers, or if there's any sorts of regulations that are being exceeded. So these are extremely accurate instrumentation, and they unfortunately aren't everywhere, but when they are somewhere, you should really be paying attention to those. So where exactly would you even go to look at this regulatory data? There's three main sites that you could go to here that we are suggesting. So we have the airnow.gov website. That's also available as an app. There's the Fire and Air Quality Map. And then there's the EPA Smoke Sense mobile app, which obviously is going to be very helpful if there's actually a wildfire in effect. It also gives you some emergency information if there is wildfire in the area. So if you were to go to the EPA AirNow website, for example, this is the screen that you would see. And it is showing, the little dots are showing the air quality index level at each of the stations that's reporting. And you can see, one thing to note here actually is that these are updated on an hourly basis. And you can note that there are a fair number of them, especially in the West and on the East. There's maybe not as many in the middle of the country. But you can see that there is very useful information. You can tell immediately, okay, well, the air quality on the West Coast is maybe hazardous, while on the East Coast, it looks very good. So there's a lot of information you can get from this website. So if we click to the next slide, another feature of it is that you can actually forecast. You can go to it and see what the air quality is going to be for the next few days. And so what it's doing here is it's using weather information and modeling to predict how the air quality is going to change in the future. So that's another really cool, useful tool. The EPA Fire and Smoke Map. So this one shows the location of the fires, the air quality at each of the regulatory monitors, and it also is showing the smoke across the country, which is shown by this sort of gray shading here. So it's a really great tool for teachers and students, so you guys could examine how the local events can have national and global impact.
And the commentary on this map that I would make is that in the other maps, and if we go back for 1 minute, the other maps show all the regulatory monitors. A real innovation on the fire and smoke map is that when we zoom to a greater level of detail, that would become more apparent, and we'll see some other images in this presentation where we show those, is that this map actually combines regulatory monitors, which are shown in circles, and they're a bit hard to see, but also some triangular sensors, which are temporary regular monitors. And if we zoom in a bit, little other symbology that are low-cost sensors. And I'll be talking about those in the upcoming slides on what is the difference between a low-cost sensor, how did they deliver data differently. I think our overall comment is that a map like this in particular, all of these maps are very useful for teaching the science of air pollution. This in particular is a wonderful tool because it shows a variety of measurement sources, a variety of types of sensors, and it adds a real sense of spatial resolution, and we'll get into that a little bit later, that you can see great details and nuance, which is very important in fire and smoke events. So that's what I'm talking about here. So when we zoom in on particular sections of the map, we start seeing more nuance. And one of the wonderful tools in this map is that any one point, be it a regulatory permanent monitor, the circles, a regulatory temporary monitor, a triangle, or one of the small sensor data, can be clicked on to reveal a time series of data at that location over a period of 5 preceding days. So in this case, I deliberately chose a point that seems to be fairly far away from the fires. And we can see very quickly that we had great air quality up through September 12th. There may have been some data outage at this location for a day. And then we see a very rapid increase in worsening of air quality and an increase in AQI levels. Note that, you know, as Olivia introduced, these color codes are consistent. So the yellows and reds and oranges here are mapped to the exact AQI levels and health effects that we discussed previously. I personally, and as an engineer and scientist, I find that displays like this are very important teaching tools because we start understanding interrelations of data trends such as spatial distribution and temporal distribution. So that is distribution of some quantity in space over the globe or over the earth, and some variation of that same quantity in time are very important to help science teachers explain scientific concepts to students. So what we refer to and haven't explained a little bit more, and we'll see more data from, are in addition to the regulatory monitors that Olivia discussed, and she already discussed that they're relatively sparse, they're infrequent because they're expensive to deploy and maintain. That creates, if you think about it, some gaps on the map. So as you noticed on the previous maps, in some parts of the country, there are relatively large distances between these regulatory monitors. And this is really, with the rise of smaller and more accessible technology, has given rise to various entities building much smaller, much more inexpensive, much simpler sensors that, because of the cost of building them being low and the cost to deploy them being low, they can be deployed amply and in more locations. So while a regulatory monitor might be in the tens to maybe hundreds of thousands of dollars, we're not talking about devices that top out at $2,500, some of which are available for as low as $100 to $1,000 more commonly. And so while they're not as accurate as the regulatory monitors, they measure the same quantity with some degree of approximation, and they're great to fill in the gaps in between. We'll talk in very specific detail about one that is very popular right now and is being talked about. And as Tammy shared with us the other day, the purple air discussion out in the school area or between parents might be something quite common when smoke is in the area. So really low-cost sensors, in summary, they improve our understanding of the spatial distribution. So where on one side we see regulatory monitors only on the right, on the left we then see small sensors that really fill in all the gaps with data that we see. And as you can quickly see in this image, the trends largely that are being shown are relatively similar. There are some degrees of magnitude changes here that we'll discuss in a minute. So because smoke and smoke events, as Olivia started with, are exceptional events, the air and the smoke during those events are not distributed the same way. They're not distributed uniformly. And we see a very, very large spatial variation, sometimes over very small spatial extents. And so more sensors are better because they help explain the variability and nuance of the data around us, right? So we do have to make the delineation that a regulator, we have, again, this is a complicated subject we won't dive into very deeply, but the regulatory agencies are legally liable to enforce national air quality standards, and they have to use instruments that can be reliable enough to defend a legal challenge. This is not the case with the low-cost sensor. Low-cost sensors are meant to provide an array of data to fill in those gaps, but they're not of such quality that they could stand up to a legal challenge. So that's an important distinction. So in particular, we've gotten many questions from many different constituencies. As a team, we answer many questions about the sensor. As a person, I have gotten many screenshots of people saying, hey, Purple Air says, ... So we really thought it was very important for teachers as an audience that may even have heard this from their students or maybe hearing this in the news to learn a little bit more about what is Purple Air, what's behind it, and how do I contextualize it? How do I not use it? And how do I use it with my students? And what are the caveats? So Purple Air is one of the small sensors that we just discussed. It falls into this low-cost small sensor category. Physically, it is a small device that is shown here between the hands of somebody hanging it next to their apartment. If we look at the images below, that is a look from the bottom up into the device. And really what it is a plastic housing that contains two identical particle sensors. They measure the same quantity at all times, and that creates a dual channel device where channel is really just the reference to the fact that each of the sensors measures the same quantity in parallel with the other. These are privately deployed. You can purchase one tomorrow and hang it on your porch. They're consumer grade PM sensors. The sensor inside uses a slightly different technique than the regulatory monitors. So they use a laser light scattering technique, or really a technique that uses a laser and light scattering properties. Yeah, Tammy's holding one up, thank you. Awesome, right? So it's a handy size, quite literally. Thank you, I should have just put you in charge of the graphics instead of Purple Air. And inside of that is a little laser particle counter. And when I explained it to my kids, my best analogy was that if you've ever driven either in rain or snow, that we can tell that the intensity of the reflected light off the falling snow or rain particles is pretty much proportional to how much of those particles are in there. The more snow, the brighter the reflection. And I think fundamentally that's about the simplest explanation of how these work. So the lasers inside bounce light off of the particles scatter that light, and we detect that scattering. And that's how these work. They can be made very small, as we saw. And all of those sensors that are purchased by individuals, and in some cases, small government agencies use them. They're connected to a data system, and that data system then displays them on this map. And as you can tell from the other map, the trends are at large. The trends are reflective of what we saw on the regulatory map, but we see a lot of the gaps filled in. We also might see some nuances and outliers and by outliers, I mean, for example, in the middle of the screen here in Indiana, I have some sensors that is in a mostly green area have a single red sensor. These may be spatial variations that are picked up by a sensor that a regulatory monitor does not pick up simply because of its location. That is the best case scenario. In the worst case scenario, this may be a sensor that's hanging right above somebody's barbecue or outside of a fast food restaurant that's emitting particulate matter all the time. And so that gets us more into the caveats. But this is what you get when you use Purple Air on the Purple Air map. It is this network of small individually deployed sensors. We'll get into this a bunch more in the actual usage guideline for those of you that might want to use this data routinely. But these are two snapshots of the same screen. And for smoke particles in particular, and this is important to note, it has been found that this type of sensor that's in the Purple Air monitor over-reports without any correction factor, basically reports a higher value of particulate pollution than is actually in existence in the air. And so when we apply that interface that they provide in their map, in a little drop-down box, lets you select essentially a correction factor, a correcting factor that changes the values. And when you apply that, as we clearly see, the numbers on the chart drop, and a value that previously reported 154 is corrected to 89. So these are significant differences in AQI as a result of a data correction. So because we see so many of our folks that we've talked to, and we see it as reasonable to assume that teachers may want to use this as a tool to both teach and to check the air quality in their neighborhood, we've actually put together a couple of very concrete usage guidelines that when you use purple air, you should definitely consider applying one of these correction factors, and especially during the smoke events. There's a lot of literature and a lot of discussion currently around which factor to use, and that as really goes beyond the time that we have available today. Our current recommendation, based on a number of conversations, is that the AQ and U correction factor is the best one to use. The other thing to pay attention to on the purple air maps is that purple air, the regulatory monitors almost always report a 1 hour averaging period because that's what the federal air quality standards are written to. The purple air monitor does not, and it can provide data on much shorter averaging intervals. So that means if within 1 hour, I have poor air quality in the first half hour and better air quality in the second half hour, that resolution can be shown by a purple air and can be selected as this averaging interval. However, sometimes when you're trying to compare and make decisions, it may be better to choose the longer averaging interval. 10 minutes is the default in order to see a more representative value of what you're exposed to. And again, that really connects these dots of Olivia having talked about that exposure. Time is an important factor. So that if my AQI was 90 for 10 minutes and the average for the hour was 50, that is an important thing to know. So that's our recommendation for correction and averaging. We also see commonly the mistake being made that the purple air network purple air sensors can be deployed anywhere. I can put it in my office, I can put it in my living room, I can put it on my porch, and the map by default shows both inside and outside sensors, and that often portrays some false data points that make it look like there's some clean spots in between spots that may have elevated values. And so we want to be sure to only look at outside sensors. Lastly, because of their spatial resolution, we often tend to think that everything that these maps show in terms of spatial resolution, meaning close together, is accurate. And the case is actually that in some cases, the sensor may be reporting an erroneous value, and it may have a fault in it. We've seen cases where sensors that are on the map being reported as outside clearly are actually inside and are simply mislabeled. So in a scenario like this, we want to caution users and teachers against making a decision that, oh, the air is clean at the spot when the data is more likely an outlier.
Bastian, if I could add one other thing on that previous slide. So something else to keep in mind is the actual channel that you're looking at. So here, Bastian's showing the US EPA PM2.5 AQI. If you're really looking to compare the purple air map to maybe something that you're seeing on the Air Now website, you want to make sure that you're looking at, you know, apples to apples, or at least at the same channel, because I believe the default for purple air is not to go to this AQI. It might show you the PM2.5 concentration or another channel's concentration, for example. So that's just something else to keep in mind.
That's a great point. And, you know, if we had a little bit more time and if we, in our post-webinar surveys and in communication with you, you feel that you would like even more hands-on guidance with any of these tools, let us know and we can set up a separate session. I had considered an actual sort of live demo of all these tools, but all of that takes some more time. And so we won't do that today because we also have some more important material to cover. One of the questions we commonly get, and I actually even got one from one of the participants, or registrants, I should say, in advance, was, gosh, you know, it's so confusing because if I look at different data sources for the same spot, I get many different AQIs. And so that prompted us to add a slide on really sort of under the topic of be careful of your AQI source. That is, where do you get your AQI? And we wanted to point out as a team that there are really two fundamentally different sites. What we've been talking about really up to this point are data generators, meaning there are entities that generate the data and then display the data that they generate. So that's what Olivia discussed, the regulatory monitors being displayed on a regulatory site. And in purple air, it's low-cost sensors from the purple air network reporting data to the purple air network. However, there are many, and we just included a few little examples here. There are many sites that simply aggregate, meaning that take in data from a variety of data sources that are open, and they put that data together and then display that data to you. And as much as we don't want to indicate that they're always wrong, that's not the message here, but there are processes that are, I call it the AQI game of telephone, that there may be processing steps that the data undergoes that aren't necessarily apparent, and that sometimes can change the values, can change the depiction of the value, and really you have to be very careful of your source. And just as an example, and I think the question actually came from Costa Mesa, so we looked at that area. This is the Fire Air Now site. It shows a pretty uniform distribution in the orange. This is at the same exact time and date. So these are parallel screenshots on the same day and time. And on fireairnow.gov, these are small sensors that are corrected. This is purple air data that has been corrected by EPA in the orange. In parallel, we see purple air without the correction showing these other values. And then we see another tool that doesn't even use the AQI scale because they have defaulted to their own scale of 100 as being the best and 0 being the worst, which is kind of the opposite of the standard AQI. So it becomes very confusing. So that's our sort of, maybe one of the sources, to the person who asked the question, one of the sources of your confusion may be the source that you're considering. And that may add to the confusion of what is my AQI. Our basic takeaway message is to get the official AQI at your area. We really do recommend going to the official sources such as AirNow and those tools. So at this point, we wanted to make a connection that is between the Kids Making Sense program and this topic of air pollution and smoke and particulate matter that pertains to you directly as a teacher. And so as an introductory element, Kids Making Sense is an educational program that again, we have built over a number of years to measure air pollution using a low-cost sensor technology. And in the program, we teach students to, first of all, learn about the subject matter. Olivia will cover that a little bit more, but take their own measurements, interpret their own data, and then really a strong element of the program is for those students to learn, how do I not just collect data, but how do I learn about the data? How do I measure the data, discover the trends, interpret them, but how do I then take action? And we actually have a forthcoming piece that we can bring to your attention about an article of a specific teacher whose class actually was able to measure an unexpected data event in their community and took the data and their findings all the way up through the chain into a regulatory agency where they made an impact. So really the program is about science, understanding the subject matter and what science is about, but it is ultimately about connecting scientific data and findings to a student's own life and their community. Practically speaking, that is more at the philosophical and at the teaching level. Practically speaking, we use a sensor called the AirBeam 2. This was created by an organization called Habitat Map. And what it is, it's a small sensor that is about the size of an extended hand. It's no larger than my hand. And in a plastic casing, Olivia's holding it up right there. Great, thank you. And inside of it is a particulate sensor and all the electronics that let this sensor be, first of all, mobile, and let it wirelessly connect to a mobile app that displays and captures its data. And that data is then stored and later wirelessly uploaded to an entire backend of software we'll talk about a little bit later, that then shows the data on a map and records the location and shows the student an exact trail of their measurement. That sensor is then integrated together with the mobile device. It is integrated into our curriculum that we have curriculum guides that have actual activities for students in a laboratory setting that could be done at home. You'll learn about that a little bit more in a minute. It has teacher guides and it is aligned with NGSS standards. So each of the modules can be referenced to one of the NGSS alignments. It has, like I mentioned, the small sensor, a data visualization platform, And it's all packaged together in a program where we use tools such as Google Meet to support you as a teacher in executing that program in your classroom and running that in your class. And maybe Olivia can, again, I work with the technology. Olivia and Tammy have worked much more hands-on with the curriculum. So I'll let Olivia walk us through a little bit of that.
Yeah, that sounds great. So the curriculum that we have, it's not just focused on the airbeam activity. It's actually a series of progressive activities where students get to learn about particles, they get to learn about health effects, the impact on the environment. There's actual labs that they can do that are associated that we provide the materials for. And they learn how to develop a hypothesis and an experiment plan as well, and then look at their results from the airbeam activity. And then arguably the most important aspect is that they get to then take that information and think about how they could actually act on it to make a difference in their community. So the idea here is really empowering the students to not only learn about the environment that they're in, but what they can do to make a difference as well. And that really will help them connect to the science at the same time.
And what will make the segue here in a minute is that the front end of the curriculum is more about understanding particulate matter, and I would sort of call them closed-ended activities that have an outcome, an expected discussion, and a finding that creates a learning moment. The latter part of the curriculum really is very open-ended in the sense that students can design their own experiment. They can say, this is what I want to explore. I have a hypothesis, like Olivia said, that I would like to prove or disprove with an actual sensor in my hand. And I think there's a real excitement in all the classrooms. I have to say that even as a science curious adult, I get a real sense of excitement, and we'll get into that in a minute. When you take the device into your hand, you turn it on, you link it up to the app, and you start seeing what's in the air around you. So that's really what go ahead.
I was going to say one other thing I was going to note about this. I mean, it's written on the slide, but just for emphasis, we understand that, teaching right now is sort of a difficult beast to wrestle with, some classes being hybrid, some being in class, some being at home. So we've adapted our curriculum to be distance learning appropriate as well. So it really can be used both in the classroom or by students at home. So
yeah, that's a wonderful point. And I actually, as a matter of fact, just today, we distributed a kit where originally some of the activities are focused on a 5-student group in a campus environment. We distributed an entire kit where part of the experiments will be done at home by the student with some parent help. Some of the experiments that are a little bit too complicated will be demonstrated by the teacher. He said that I'm going to show them, they're going to watch me on video. And we are distributing individual devices to students, and they will be able to do this measurement at home. They will then disinfect the device that's included in our kit. They will return it to the class, and they will be redistributed to other students. So it's really happening, and it's exciting to see that this is actually a very adaptable mobile laboratory in a sense that we can use. Where we wanted to really, and we really didn't want to go too deeply into the program and sort of at a marketing level. What we really wanted to do is connect the activities and the equipment back to the subject matter that we're talking about. And so we wanted to spend a few minutes covering here in the final, we have about 10 minutes left in our presentation section before we go to Q&A, is talk about some of the experiments that we have run using our equipment and using the website, and how that may be first of all, maybe the experiments themselves can be useful to you as a teacher. We have started distributing some of these things as material, as content that you could use in your classroom without having the equipment, just to discuss the findings. And we also wanted to point at the types of activities that, whether you're on the West Coast and you're in smoke, or you're somewhere else in the country and you might be seeing the effects of smoke, would be really interesting for you to do. We are just starting a trial with a teacher in the Midwest, in an area that's generally not affected by these fires, but it will be very interesting to see if a group in that area of the country can actually detect wildfire smoke that we saw on these maps before. So what we did in one of our experiments, and I think the way we're gonna skin this is Olivia did part 1 and I did part 2. So Olivia, you wanna talk us through part 1?
Yeah, sure. So This was, you know, a few weeks ago when it was very smoky outside. I live in a place where there was actually a fire not too far away. It was maybe 10 miles down the road. So it definitely impacted us. So what I did was I took the air beam and I wanted to know, first of all, what is the concentration or what are the levels of PM 2.5 in my actual house? I don't have an AC system. We didn't have an air purifier. So I really wanted to understand, what am I breathing in? More importantly, what are my cats breathing in? And then also, what are the concentrations outside? Because it was extremely smoky at that point in time. So I, you know, turned on my air beam. I started a measurement session. I was standing inside. So at point A, before point A, I was inside my house, you know, on one side of the door. I then opened the door at point A and I walked outside, and it actually went off scale. It went into the hazardous range. Because the concentrations were just so high. I stood outside for probably too long. And then at point B, I came back inside and wanted to see sort of what the levels were again inside, if me opening the door had made a difference. So you can really see that at least being inside with the windows and the doors shut, in my case, was helping somewhat. I mean, we were still at quite high elevated levels inside, but definitely nowhere near as bad as outside.
And I would have to say, I've run probably 15 different experiments, and I would say the majority of my findings during the last month have been very similar to Olivia's. So that is probably the most common scenario that we will find. However, I did find on one of the occasions, again, hypothesis and finding finding the unexpected is just as important to science as finding the expected, is that in one case, the experiment I ran is that prior to point C on the chart on the right, and we'll see in a minute where that chart comes from. On that chart, prior to point C on this, I was indoors. This was a morning time overnight. I then walked outdoors, and the air outdoors was actually cleaner, dipping into the green AQI levels until I walked back in the house at point D. And so in this case, while the differences were marginal, admittedly, but it is actually scientific evidence that in certain scenarios, your house can actually act as a container of worse air pollution while the air outside is already cleaned out. So this is a great example of two different hypotheses, experiments, and findings that help us understand and ultimately point to science. I also ran some more complex experiments. In this case, I had assistance and I had the mobile sensor in a vehicle. Initially, the sensor was actually in the car. It showed some different effects of the effectiveness of filtration in the car. On that day, it was fascinating that, as you can see from the terrain map, that the pollution values down in the valley, this is in the Northern California area, were actually lower. And as we started driving up the hill, we started getting into very, very high air pollution values, AQI values. And so this is a great example of an exploration that shows you what we call a smoke aloft scenario, where smoke has now been driven up into a higher level in the atmosphere and sits up above, and only areas that are higher in elevation would see elevated concentrations. So all of that, just as a closer here, when you do an experiment using this air beam sensor and you use the map that's part of the program, the data is automatically uploaded. So one of these indoor-outdoor comparisons, basically, you see the locations of the measurement directly on the map. You see this time series chart directly on the map, and this takes literally 0 interactions, because at the end of the mobile session, this data is uploaded automatically. This is shareable. This data can be shared by a student with their class. This data can be shared with their student in this format with, like we said, in the cases where we have an unexpected finding, we can even share this data with a regulatory agency or school administration. So that kind of brings us to a connection point of closing out with the topic of smoke in general. Wrapping up here, we hope that the resources we provided in recap, we really recommend that in smoke events you rely on regulatory grade measurements, that you consult some of the key sites in assessing the data quality in your community, that you have various resources, some which use the large sensor network, the official regulatory monitors, some which show you the small sensors, and that you can use those to assess your own safety and the air quality for your students. You can share those resources with students. And then there are also ways through this curriculum and with small sensors that you can actually assess the air quality in your immediate surroundings and integrate that into your learning. So I think we're just about coming up on the time here that we wanted to reserve for Q&A. So in wrapping up, I wanted to thank my co-presenter, Olivia, and I wanted to thank you for attending. And I guess we'll go through and see if there's any questions in the Q&A panel.
So there've been a few questions in the Q&A panel, it seems. One that I wanted to actually address out loud. Let me just scroll to it. Question is, can we expect a different or an opposite trend on the East Coast where the AQI is green outside? And I just wanted to point out that although we're talking about wildfire smoke specifically here, there's no reason, in fact, the curriculum wasn't written specifically for wildfire smoke. We can just apply it to wildfire smoke. But there are a number of indoor activities that could actually cause your indoor air quality to become worse than the outside air quality. And so there's a number of experiments that students could do that focus on that would also be very informative and also help them to understand how what they do indoors can affect the air that they breathe. So that was a great question. And then another question was about sort of what's the best approach to take to not depress students? Because we've been inundated with smoke for, a number of weeks here. How can we teach them about the air and not, in sort of more of a uplifting and positive way? And so my response to that, and Bastian, feel free to chime in as well, is that I think really focusing on empowering the students to empower them to, first of all, understand what it is that they're breathing, why it's happening, but then also empowering them to make a difference. So there are things that they could do maybe inside that will help improve the air that they are breathing indoors. There are different strategies that they might be able to employ, closing the windows, or, if there's an air filter, or if you can build your own air filter, there's some tricks out there to building your own one that you attach to a box fan if you don't happen to have an AC system or something. So there are a lot of different strategies, and I think really empowering them will help them feel like they're making a change, which will also lift their spirits.
I very much concur. I think that's a wonderful answer. I personally find that the fire.airnow.gov map provides such a level of resolution that creates, if you're in the affected area, so let's frame that. I think it depends on what part of the country you're in, but if you're in an affected area especially, these sensors give a much greater sense of what's around you, and even if that's negative, understanding it. And I think there's a greater sense of anxiety when I'm seeing a red dot that's 40 miles away from me, and I don't know what my air quality is right next to my house, than seeing the trends around my house. The small sensors also give us a sense of improving trends in some cases more quickly. That may be an aspect to just focus on, and it may be a philosophical exercise on focus on what Olivia said. Understanding the phenomenon in your proximity is very valuable and shouldn't depress you in the sense that knowing what's around you empowers you. So great question though, and certainly a challenging one. I'm also reading, Tammy, thank you for going through. Tammy answered a lot of these questions. One of the latest questions here is relatively complex. It revolves around low-cost sensors in a particular geographic area. The best answer I can give to that without giving a definitive answer, that there are many reasons. So the question, I guess I'll read it real quick. An ongoing debate in the local community and on the Nextdoor app, which is a social network, about which is more accurate in a hillside setting, Purple Air or AirNow. Argument favoring Purple Air being that the sensor from which AirNow data is drawn along with the waterfront is not reflective of air in the hills. So I think we have to be very specific when we talk about AirNow, what resource we're talking about. First of all, if we're talking about the regulatory monitor located far away, there may actually be significant differences between what that monitor measures in its location and what's present at your location. We showed an example of that in a minute with this little drive test, even that a valley location saw a lower particulate measure level than a hilltop location because of a smoke aloft phenomenon. So that may be the case, right? When we look at air now, there are also different data, like we explained today, that you can be looking at. So I would encourage you going forward to look at that fire.airnow.gov, because it actually combines the two measurement and corrects the purple air data. So if you pull up the map for the Berkeley Hills, you'll see all the purple air measurements on the fire.airnow.gov site as little squares. They're delineated differently, and they're already corrected using a specific correction factor that EPA has developed. And I think that would be a better comparator than generically looking at the regulatory monitor farther away. So I know that's not an answer for all scenarios, but I would encourage you to be very careful what data you look at to make the comparison, and using the closest EPA corrected low cost sensor would be a very good option for you.
And then there was a question about the slides, and yes, we will send the slides out to everyone that was in attendance. Let's see.
Yes, so, you know, I think the last one was more of a statement than a question, which is that we have been inundated. I certainly, you know, feel for all of you. The students are inside. We're all inside. It's harder to get outside on the few moments that we can. So as Olivia responded, it's easy to get depressed. The one thing that I found heartening is that understanding the data also then helps us predict. So don't forget that all of the sites that we mentioned, except for the fire.airnow.gov, that is not a forecasting tool. All of the tools that we mentioned, AirNow, have forecasting tools. And I think on the positive note, in the last 3 days, we've seen a huge clearing trend. It may be temporary, but a huge clearing trend that was pretty clearly indicated both by purple air, if you knew what you were looking at, and were also indicated in these forecasts. And so on Monday, there were forecasts that the air was going to clean on Wednesday. So that can be a great tool to sort of ward off the slump and the feeling of being inundated when you know something is coming, something better is coming. So in closing, again, thank you for attending. We do run webinars that go into the program components, how to run a program, how to fund a component regularly. So we encourage you to visit our website. That is kidsmakingsense.org. There is a webinar sign up page where we have future webinars listed. We also really encourage you, all of us here would love to have you follow us along on the social media. Over the recent past, we've posted lots of different ideas, news sources, scientist digested news pieces that provide some content and context to what's in the news, and even some activity ideas, whether you have an air beam and a classroom kit or not. And so we really would encourage you to follow us along and give us a thumbs up here and there, and give us feedback on the types of things that we're posting. With that, I think we will go ahead and close things out. One of the last items that I can point you to, in addition to our email addresses, feel free, we'll distribute the slides after, feel free to contact us with questions. We've also released a new help desk website that is at help.kidsmakingsense.org. And in that is a section with some FAQs on the program that, if you're more curious, you can also start there with answering some of your questions about the program. And so with that, I want to once again thank you for attending, and thank my presenters, and give the mic to Olivia for a final closeout.
Yeah, I'll just say the same. Thank you so much for joining. And if you do have any questions, feel free to reach out at any time.
Thank you, and a good evening, and stay safe from all the smoke out there.
Thank you all.